So in our last video, we've talked about different ways to make alkynes. Um, Now let's start thinking about ways in which we can actually use them to do reactions. And one of the most common ones to see is going to be an SN2-like reaction where we use a base. Cool thing about this is a really common base is going to be our sodium amide, the exact same thing that we used in our last one to do our terminal halide, or sorry, our terminal alkyne formation. That can actually deprotonate our alkyne. So if we think of our alkyne at the terminal, we have that hydrogen at the end. Our sodium amide, our NH2 minus, Na is just going to be our spectator, can do acid-base chemistry where we remove a proton and then generate what is known as a acetylide. That's just going to be the triple bond. That's the YL acetylide anion on so our lone pair at the end of our triple bond. And then our NH2 would become NH3. This right here is a gas, ammonia. And what will happen is this will actually bubble out of your reaction. And with regards to Le Chatelier's principle, when we think about this equilibrium here, if we are losing our products, that's actually going to keep driving our reaction more towards the forward direction. So what will happen is this will just keep going and going and going as our ammonia keeps bubbling out. And that will do a really good job of getting us the deprotonated version, or this reactive intermediate, this anion with a lone pair at the end of your alkyne. Now, this will actually be the major product that will actually form from like our last ones. So like if we kind of think back to our last video when we made like this terminal, this will actually form that system all the way. And then what you'll do is you'll actually typically use a anything to quench. So sometimes your solvent can quench. Often you'll just add like, for example, acid or water, and that will then just protonate to give you your ultimate product. Now, this deprotonated alkyne will serve as a really good example of a nucleophile, and we can do a bunch of types of reactions with it following kind of a traditional SN2. So if we look at this alkyne here, so we have 1, 2, 3, 4, 5 carbons and then a methyl. This is a terminal alkyne. And if we do a multi-step reaction where the first thing we do is we add our sodium amide, which is going to be our strong base, that will remove our proton on our alkyne. That is going to be our most acidic. Remember that the more S character something has, the easier it will be to remove. So that proton is going to be more acidic than any of the other ones. That would then give us our deprotonated product, which will serve as our nucleophile. And this nucleophile can attack an electrophile via traditional SN2. So if we imagine here a 1, 2, 3, 4 carbon, so this is going to be a bromobutane. This can come and attack via backside attack at where our leaving group is, and then kick out our bromine. This looks like a weird nucleophile. We're normally thinking of nucleophiles as being something a little bit smaller. However, it behaves the same as a nucleophile, and this can come and do an addition. So if we wanted to draw a product for this type of reaction, we would draw our starting material. I now have a new bond, which is then going to have our 3 carbons system. So this new bond right here comes from this set of electrons right there. And then I have my butane and then my starting material. Now, this is a backside attack, which we normally think about inversion of stereochemistry. However, our product is going to be our linear sp hybridized single bond, so we don't actually draw any. And this just behaves the exact same as a kind of normal SN2 reaction. So anytime we have a terminal alkyne, we can use our sodium amide base and then have this come and attack at our leaving group. Now, this can also add to carbonyls. we'll spend an entire unit. That's going to be unit. Is that the next unit? No, the one after. Unit 5. Unit 5 is going to exclusively focus on carbonyls, so we'll talk a ton about attacking carbonyls. But we can actually get the same thing to happen on carbonyls because they're going to be a good polar bond. So to kind of show you an example, here we're going to use a terminal alkyne. We're going to react this with a sodium amide. That's going to be our strong base, which will deprotonate. We can then react here with an aldehyde, and then we will then quench with acid. So that's kind of like slew of things, which will kind of add sequentially. So if we imagine here, we start with our protonated version. If we use our strong base, so here this will be our NH2 minus, this can come and deprotonate, giving us our reactive intermediate. This is going to be our really, really strong nucleophile. This strong nucleophile is going to want to attack our most delta positive spot. If I think of my carbonyl here, I know my oxygen will be delta negative and my carbonyl carbon will be delta positive. This is going to have a dipole that's going to be pointing upwards towards that oxygen, making this carbon a really, really good point to attack. So if I imagine a reaction here where my alkyne comes and attacks my carbonyl carbon, it can push the oxygen up to make a lone pair. This can give us a new bond that is formed between our triple bond and our carbon, which will have, in this case, our O minus and then our methyl. In this case, we can then do an acid base. So here we'll just do a generic H plus, which will protonate and make an alcohol. So this is another type of reaction that we could do with alkynes. You'll see it behaves pretty similar to an SN2, where we have something that's going to come and attack. Instead of your leaving group leaving, because of the fact that it's a carbonyl, it's going to go from a double bond to a single bond, and then we can quench to form an alcohol. This will be a pretty common type of reaction that we'll see, and is actually really helpful to kind of like make your molecule bigger, because this is a way where we can add carbons. One of the things that you might want to do potentially in the future is thinking about, well, how can I get rid of this alkyne and get it maybe down to like a single bond, for example. And that's actually going to be kind of like the focus of our next set of videos. What are reactions that we can do to add things to our triple bond? That's kind of a quick summary of our kind of main takeaways. Anytime you have a terminal alkyne, we can use a strong base. The sodium amide, or NaNH2, will be the most common that we will use. That can go through deprotonate, giving us our acetylide anion. That can serve a really good nucleophile and do all kinds of things. It can do an SN2, kicking out our leaving group, or it can also attack a carbonyl. Those are kind of two specific examples that we talked about in here. So we're going to stop there, and I'll see you in the next one.